Swayam Prabha. Digital India. Educated India.
Okay, we'll begin. So, in the last lecture, I discussed about absorption in tray column. A tray column is one where there are trays placed at a regular spacing, and the gas and liquid are allowed to interact and separate and then leave to the next tray. So, it is held in a stage wise operation. Okay, the gas liquid contact happens in a stage wise manner. And then we also showed how to find out the number of theoretical stages. Okay, so a theoretical stage is one where the leaving compositions are in equilibrium. Okay, for example, if I have to draw one particular stage, so let's say this is the nth tray. Okay, so liquid is coming from the top, and then some level will be maintained here, and then the liquid comes down, and the gas goes here, leaves there. So, in terms of our nomenclature, this would be Yn. The composition in the gas phase leaving nth tray is Yn, and then the composition of the liquid leaving the tray n is Xn. Okay, the gas that is incoming to this nth tray is Yn plus 1, and the liquid that is coming in is Xn minus 1. Okay, so this is a nomenclature. So, with respect, so I am talking about a tray column. The trays are numbered 1, 2, 3 and up to n. So, I am talking about one particular tray, nth tray, and then I am defining the compositions. Okay, so this is the liquid column, and then gas bubbles through this column. Okay, and then phase separates. So, here we define something called an ideal stage or ideal tray or theoretical stage. Okay, these are all equivalent terms. So, this is a one where the contact between the liquid and gas is allowed to contact sufficient times, so that the outgoing streams are at equilibrium. Okay, meaning this Xn and Yn are in the equilibrium line, and they follow this relationship. Yn is equal to m times Xn. Suppose if you assume a Henry's law kind of equilibrium line. Okay, this is what we call as an ideal stage. If I make this assumption, then I can calculate number of ideal stages required for a particular operation through a staircase construction or through analytical means. Those were the topic of discussion in the last class. But in reality, no stage is an ideal. Okay, so the outgoing compositions will not be at equilibrium following this equilibrium relationship. They will be always falling short of that equilibrium compositions. Okay, so that's a maximum concentration change you can achieve, but it's not going to happen because this tray will have a limited dimension, limited contact time. Okay, because of which there won't be a ideal operation possible. So, it's going to be always non-ideal or real. Okay, so I'm going to define, to characterize this realistic operation, we are going to define something called a tray efficiency. Okay, so tray efficiency is defined to account for how much is it away from the equilibrium compositions, or how much is it away from an ideal stage. So, there are many means of writing tray efficiency. We are going to use what is called this Murphy tray efficiency. Murphy-Trey efficiency, and we will use a symbol EMG. This letter E refers to efficiency, M here refers to this name Murphy, and G refers to the definition of the efficiency with respect to gas phase composition. You could also do the same thing with respect to liquid phase composition, in which case it would be EML. Okay. So now the way we define this Murphy efficiency is the actual change in the stage. So that would be yn plus 1 minus 1. With respect to nth stage, the actual composition change is yn plus 1 minus yn, because yn plus 1 is the incoming composition, yn is the outgoing composition. So this is the actual change over the maximum change that is possible. What is the maximum change that is possible? That would be yn plus 1 minus yn star, and this yn star is the one that is in equilibrium with xn. Okay. So yn star is in equilibrium with xn. Okay. So by this definition, for an ideal stage, EMG will be equal to 1, right. For an ideal stage, the actual composition change and the maximum change possible are equal. So the Murphy efficiency will be always 1. But in reality, this yn will not be always equal to yn star, it will be much lesser. Therefore, the efficiency will be less than 1 for a real stage. Okay. So for a real stage, EMG can be less than 1, because yn need not be at yn star. Okay. So let me show this pictorially. So this is y versus x. I will use straight line for the equilibrium line as well as the operating line. This is equilibrium line, and let us say your operating line is this, and nth stage may correspond to this. You see, this is a point which is xn comma yn. Okay. This is yn plus 1 and this is xn minus 1. So this point yn and xn minus 1 is this, the composition before above this tray, that is yn and xn minus 1, that point is noted here, and the leaving compositions are the other side of the tray, the compositions are xn and yn plus 1, that is this point. These 2 points lie in the operating line. Okay. So when I look at the change between yn to yn plus 1, the outgoing streams which are xn and yn can be found in the operating line. This is what I call as an ideal stage, corresponding to a Murphy efficiency of 1. Okay. So this is for an ideal stage. So now in real stage, so this is your equilibrium line and this is your operating line, and you will see that this point xn comma yn need not be on the equilibrium line, it can be little above. Okay. So this is xn, this is yn, and this is yn plus 1, and this is xn minus 1. So you can see the difference between these two. Here in the ideal stage, the leaving composition xn and yn lie on the equilibrium line, whereas in a real stage they are slightly above that equilibrium line. So in terms of the Murphy efficiency, what we are saying is the length, the ratio of the length between yn plus 1 to yn plus 1 to the point where it can actually be at equilibrium. Oh, sorry, it should be here. So this is yn star, which is at equilibrium with xn. So the ratio of the length between this length and this length is the Murphy efficiency. So the maximum possible composition is yn plus 1 to yn star, but the real actual change is yn plus 2 yn. Okay. So if I look at the ratio of these two lengths, that would be the Murphy efficiency with respect to gas phase composition. So now, how do we calculate this Murphy efficiency? We can actually do a mole balance about one particular tray, another tray, and we can write the equations, because we know that the gas phase change composition should be equal to the rate of mass transfer. Based on that, we can find out an expression for the Murphy tray efficiency. Remember, we are talking about efficiency for a single tray. This tray could be anywhere. So let's find out an analytical expression for Murphy efficiency. So this we will do for dilute mixtures. So if I do a mole balance, so we'll keep in mind that we are talking about this particular So let me show this stage in a simplified manner. So there is a stage in which a column of liquid is, let's say, H. Okay, so this is nth tray. So the incoming gas and liquid compositions was shown here. So now let's say that in this particular column of liquid, we will assume that the gas and liquid are well mixed. Okay, so then the mole balance can be written such that G dy. Okay, so that should be equal to Ky A y star minus y into dH. So where G is the mass velocity, the molar flux, moles per unit area per unit time. Ky is the overall gas phase mass transfer coefficient. So A here is the interfacial area per unit volume of per unit volume. So dH is a small section in this entire column. Okay. So if you take a thin slice of a liquid layer, okay, of length dH, of height dH, then this mass balance should be followed. What this mass balance means? It means the actual change in the number of moles of the gas, the solute in the gas phase, must be equal to the rate of mass transfer. Okay. So here I am using the overall mass transfer coefficient, hence I am using the overall driving force. Okay. So the driving force actually is written y minus y star. Okay, but then I have to put a minus sign here, so I have absorbed the minus sign here. So that's how it looks like this. So but you can go back to the mass mole balance we have written before for a packet column, you will see something very similar. Okay, even though this operation is stage wise, but within a single tray column, the contact is quite continuous within one single column. So I can write the mass mole balance very similar to the way I wrote for packet column. Okay, this is written for one single stage having a liquid height of H. Within that I am doing a shell balance. So now we can integrate these equations. Dy by y star minus y is equal to kya by g dh, and then this integral is from 0 to h. So, we say here it is 0 and here the height is h, because I am doing only for one single stage. This is per stage calculation. So, when h equal to 0, y is yn plus 1, and when this is h, you will have this is yn. Okay, so these are the bounds. So, we can integrate this, we will get minus ln of y star minus yn by y star minus yn plus 1 is equal to kya g and h. I will take the minus sign to the other side, then I have minus kya g times h. So, what I am hoping is to rewrite this form into the definition of Murphy efficiency. So, Murphy efficiency is defined as yn plus 1 minus yn, this is actual change by the maximum change that is possible, that is this. So, I want to rewrite this term in this way, so that I can introduce EMG in this formula. Okay. So, let us say if I find this term 1 minus yn plus 1 minus yn by yn plus 1 minus yn star. So, I will get so, you can see that this term is exactly this term, right. So, what I can do, I can for this particular term, I can use this particular term, and this is nothing but 1 minus our EMG. So, what I am trying to say is that this particular term is not in the form of the Murphy efficiency. So, I am trying to rewrite it. Okay. So, if I and I am looking at the definition of Murphy efficiency, and these two do not match exactly. Okay. However, if I write 1 minus EMG, and that term seems to be this. So, I can replace the logarithmic term as 1 minus EMG is equal to minus kya by gh, right. So, from here you can solve for the Murphy efficiency. So, that will become 1 minus e power minus kya gh. Right. So, you can see that this efficiency, Murphy efficiency, depends on many of the geometric variables as well as the operating conditions. For example, it depends on h, how much height you are going to provide for the liquid column to be available in the gas liquid contact. It also depends on the gas molar flux. It also depends on the mass transfer coefficient and also the interfacial area. How do you control interfacial area? You control the interfacial area by controlling the perforation size. Okay. So, if you make the perforation very small, you basically create very small bubbles. When you create very small number of bubbles, the amount of interfacial area can be increased. Okay. So, these are the operating possibilities, and if I make this entire term here large enough, okay, then I can achieve the Murphy efficiency close to 1. I can approach ideal like stage. Okay. So, what we can do, we can either increase h, increase the liquid height column in the design of the tray column. Okay. So, you see in the tray column, if I go back to the design, see there is a, yeah, here. So, there is this picture is not very neat, I think. Let us see. Yeah, this is the best one. So, if you look at this particular design, you see there is a small wire here, there is a liquid leveler. If I increase this, I can increase the level height. Okay. So, it is a design parameter. When you design your tray, you can design such a way that the liquid column height can be increased. But if you increase the liquid column, the pressure drop also will go up. Okay, so these are the compromise we have to make. So you don't want to operate a very high pressure drop. At the same time, you have to provide enough liquid column height so that the mixing can happen. Okay, so that's the compromise we have to make. So H we would like to increase as much as possible, but not affecting the pressure drop too much. And Ky, of course, we want to have very high mass transfer coefficient possible, and we want to have this interfacial area as high as possible, again by manipulating the perforation size or having some good mixing. And then we want to have G small as possible. Okay, so all these things will actually affect your Murphy efficiency. Now when you look at this term, you can see that we have this term Kya by G. Okay, what does this mean? This term, the group of terms we have defined somewhere before. This is the inverse of the height transfer unit, right? So if you remember, we defined in the packed column, we defined this HTOG as G by Kya. So here what we are talking about is the inverse of this, right? This is basically the inverse of HTOG, right? Now when we write the packed column, we wrote that the total height of the packed column is the product of HTOG times NTOG, right? So this is for packed column. Suppose for the tray column, if you write the height of the single stage H, if I can write this as single stage, okay, for a single stage I can write the height of this single stage H as similar to packed column, because within a single stage the contact is continuous. Okay, so I can use the same formula. The height of a single stage can be written as a product of an equivalent HTOG and NTOG. Okay, so then I have the HTOG is written as before, G by Kya times NTOG. So now you see in the Murphy efficiency we have group of term which is nothing but H by HTOG. H by HTOG is equal to Kya by GH, and that is nothing but NTOG. So then I can rewrite this equation in a more simpler way as 1 minus e power minus NTOG. Okay. Now this is all this analysis is with respect to a single stage, and then we see that a single stage efficiency can be less than 1, and we also look at the means by which we can increase this efficiency by changing these operating variables: height of the liquid column, mass transfer coefficient, interfacial area, and gas mass flux, mole flux. Okay, but now we are interested in the total operation of the entire column. Okay, so we sometimes define what is called this overall tray, overall efficiency. Okay, right now we talked about only a single tray, but then there are many trays in this entire column. Okay, so we can define what is called overall tray efficiency. So when I say overall, I mean for the entire column. And this is basically defined as the number of ideal stages by the number of real stages. So if the Murphy tray efficiency is same for all trays, we can get an analytical expression for this overall efficiency. So, I will give the expression without deriving it. So, this would be the expression for the overall tray efficiency, which is defined as the number of number of ideal stages over the number of real stages. Okay. So, in the case of design of a tray column, we can easily find the number of ideal stages that can be obtained. Now, if I know the overall efficiency, from there I can calculate the number of real stages. Okay. So, the design of a tray column absorption involves two steps. First step, you assume that each tray are ideal, calculate the number of, find out the number of ideal stages graphically or analytically. Then also find out the efficiency, overall efficiency. To calculate the overall efficiency, use this formula, which involves the absorption factor and the individual tray efficiency. Okay, and the individual tray efficiency you are going to calculate based on this. Once you know the overall tray efficiency, and you can calculate the total number of real stages. Okay, and that completes the design of tray column absorption. Okay. So, graphically, so the way you would calculate the number of theoretical stage or number of ideal stage is by going horizontally here and then vertical, horizontal, vertical, like this. So, this is first stage, second stage, third stage and fourth stage also. Okay. So, this is equilibrium line, this is operating line, and this is how you calculate the total number of ideal stages. When we calculate the real stages based on this efficiency, what graphically it means is, so you start from here, but you do not go and touch the equilibrium line, it somewhere falls short of that. Okay, and then you go up, and then you go further down, and then somewhere here you stop, and then go further like this. Okay, because this is the extent by which the actual mass transfer happens, and you never reach the corresponding equilibrium line. Okay, so this would correspond to a real stage calculation. So, this is equilibrium line, this is operating line, and 1, 2, 3, 4, 5 and so on. So, okay. So, because that this trays are not real, the number of stages would be always more than the number of ideal stages. Okay, because the outgoing composition are never in the equilibrium line when we deal with the real system. Okay, so that's the analogy. So, yeah. Okay, so that kind of completes the discussion on the efficiency. So, to summarize, in the case of tray column absorption, we can define a tray efficiency particular for one particular tray, and that is defined based on the actual composition change over the maximum composition change. The maximum composition change is nothing but yn plus 1 minus yn star, where yn star is the equilibrium composition with the outgoing liquid xn. Okay. So, I showed that for a single stage, we can write the mole balance equation and obtain an expression for the Murphy tray efficiency that goes as 1 minus e power minus kyag by G times H. Okay. And then if you want to introduce this concept of NTOG and HTOG, we can show that the EMG can be calculated by this expression. Okay. So, you are going to get the individual tray efficiency, and if you assume this tray efficiency is constant for all the trays, then we can calculate the overall efficiency by this analytical formula. Once you have found the overall tray efficiency and the total number of ideal stages, you calculate the total number of real stages. Okay. So, that is it. So, we will stop here and